If I were to tell you an inverse of an exponential function, what would you say?
Log.
A logarithm. And Joseph says it like a cuss word, but it's not bad. Logarithmic functions. They're not awful. They're just inverses. Okay, we looked at last week, how do we rewrite from one form to the other, right? Exponential function versus logarithmic. Today it says, just as we graph previous functions, or just as we have graphed or can graph, we can also graph logarithmic functions. Okay, and we kind of looked at this at the end of last week. We looked at the benefit of changing values from an exponential graph. Y'all remember it looked like this? To a logarithmic curve that looked more like this. What are some of the benefits of taking data out of exponential mode and putting it into a logarithmic picture?
You can see it better.
You can see it better. You can see it better. Sometimes, depending on the exponential function, the data outgrows the picture really, really fast. And so if I'm looking at something in a logarithmic setting, I can kind of see what's happening for a longer period of time. I can analyze this data a little better. This data right here on an exponential curve gets really hard to see because there's not very much change. Okay, so sometimes a logarithmic look at it is better. It says, because exponential functions and logarithmic functions are inverses of each other, we would expect the characteristics of the input and output values to become the characteristics of output-input values on a logarithmic function. So if I'm looking at input-output on an exponential, when I graph it as a logarithm, I expect it to become output-input. Does that make sense? Okay. So for exponential functions, over equal width input value intervals, the outputs change multiplicatively. Yeah, I need y'all to zoom in on that word, multiplicatively, right? So what that's saying is as x is increasing at the same rate every time. So what's happening in my x values right here? From 1 to 3, we're going up 2, up 2, up 2. So that's what this means, over equal width input values, okay? Each x is increasing by 2 every time. So what's happening in y? I'm going from 2 to 4. It's doubling. It's increasing multiplicatively. So we're not adding 2 every time. We're multiplying by 2 every time. This is indicative of an exponential function. They're really challenging me today with these words. Multiplicative. I feel like I'm reading Isaiah or something. It's fine. All right, for logarithmic functions, these two properties of the input and output values are reversed. So what should we see? It says, notice how the input values are now changing multiplicatively. The input values are. Can you see it? Now my inputs are multiplying by 2 every time. While my outputs are doing what? They're just adding by 2. What that means is they are equal width input intervals, or these are equal width output intervals. I need you to become familiar with this language because I think part of the problem we have with multiple choice testing is the language, right? What does this mean? Over equal width value intervals. That means increasing by the same rate every time. The twos right here. This is indicative of a logarithmic function. Okay, so if your y values are doubling, it's exponential. If your x values are doubling, it's logarithmic. Can you see that? Okay, let's go on to the next page. Some of you are looking at me like, no.
I'm going to write that down.
Yeah, if your x values are changing multiplicatively, that would be logarithmic. If your y values, your outputs, are changing multiplicatively, that would be exponential. Yeah.
What was x values?
Logarithmic. So if x's are multiplying, or if input multiplying, it's logarithmic. If your output is multiplying, it's exponential. Okay, so looking at example 1, they say selected values for several functions are shown below. For each, determine if the given function could be logarithmic, exponential, or neither. And these hold true if we're looking at equal intervals. Okay, so look at this first example A. Look at my x. X is increasing at the same rate every time. Plus 1, plus 1, plus 1. So these are what they call equal width input intervals. Equal width. That means this distance between them is the same every time. So what's happening in my y values? Okay, we don't divide by 2. We do what? Multiply by half. So these are multiplicative changes. Can you tell? Each of these is being multiplied by a value of half. Question, is it growth or decay?
Decay.
This would be exponential. That's the question that they're asking. I'm asking if it's decay or growth, and you said it's decay. Is the function increasing or decreasing? Decreasing, hence the name decay. It's decreasing. Concave up or down?
Down, up, down, down.
Concave up, because it looks like a cup, like this. Concave up. It's going to be decreasing, but concave up. Okay? It's above the x-axis. Cool. All right, moving on to B. What are my x's doing?
Increasing multiplicative.
By what? By 3. Increasing multiplicatively by a factor of 3 every time. What are my y values doing? Increasing by 10. So we do have that equal width interval business. So if my x's are multiplied, this is now logarithmic. This one is logarithmic for part B. What about x and p of x? What's happening? Neither. What's x doing? By 10 every time. Multiplying by 10. Multiplying by 10. What about y? Multiplying by 2. I don't have any case where both multiply. Okay, so this is going to be neither on letter C. And the logarithmic one would be concave down, like a frown.
B or D?
B.
Yeah.
How about D? What's happening on D? X is multiplying by 2. It's doubling every time. What's y doing? Decreasing by 3. So again, with the equal width output. So this one is also logarithmic. Good. Good, good, good. All right, so now we're looking at exponential and logarithmic functions as inverses, okay? We talked last week about this. We said if I use a composition of inverse functions, what? If I use a composition of inverse functions and I do f of g of x and I evaluate, what should I get? X. If the two functions are inverses, look right here. If the two functions are inverses and I nest them inside each other, like we did last week when we did composition of functions, f of g of x or g of f of x, it doesn't matter which one's outside and which one's inside. The result should be x. If they are truly inverse functions, then the composition of them will give me x. Okay? Says graphs of inverse functions are reflections of each other over the line y equals x. If the point x1, y1 is on the graph of f, then the point y1, x1 must be on the graph of f inverse. I should be able to swap input and output on an inverse function. So example 2 says, let f of x equal 3 to the x power. I'm going to make that red. Let f of x equal 3 to the x power. Let g of x equal log base 3 of x. G of x is equal to log base 3 of x. Show that f and g are inverses by showing that their composition gives me x. Okay? So for the first one, f of g of x. So I'm going to start off by writing my f sentence. My f sentence says raise 3 to the x power. And instead of raising it to the x power, I'm going to raise it to the log base 3 of x power. You with me? Okay. So how do I handle this 3 to the log base 3 of x? You could. He said log it. Yes. Jenna's thinking a lot easier than you guys are, but you could log it. You could. I mean, I'm not disagreeing with you. In fact, I'm wondering if we shouldn't. What you should know is that if I have a base of 3 raised to a log with a base of 3, then those are going to cancel. That makes 1. Because we learned earlier this year that log base 3 of 3 is 1. This is 3 to the first power, giving me 3. Right? So if I have a base of 3 and an argument of 3, then my answer, what power, would be 1. Right? But I want to kind of revisit what Joseph is saying back there. He's saying log it. Okay, so if I have 3 to the log base 3 of x, okay,
Would you have to log base 3? Log base log.
you would do... Man.
The only reason I picked this, folks, is if you set it equal to 0 or x, which is what I think I did in my head when I said log.
You want to leave it alone?
She's going to be questioning it. She's going to be questioning it.
Yeah, we're going to come into log and start
It's like you saw it.
I don't like it. Yeah, you should. Fun fact is that if you have a base and a power that are the same, it's 1. Okay, let's look at the G one. G says log base 3 of x, and instead of x, we have 3 to the x. Right? This one's a little easier to see. Can you see that your argument and your base are the same here?
Yeah.
Okay, so again, that makes 1. What's left? X. On the first one, what was left?
It's going to be bugs day, isn't it?
Yes. To be continued. We'll come back to it. All right, let's go on to example 3. It says a portion of the graph of the exponential function k of x equals 2 to the x is shown on the graph below. Sketch a picture of the inverse, k inverse of x, which would be log base 2 of x, on the same picture. So what we want to do here is we want to mark some points that are easily visible on this graph. So, yeah, I see that 0, 1. So on the logarithmic one, I know it's going to go through 1, 0. Do you see what I'm saying? This one approaches the x-axis to the left, but never touches. My inverse function is going to approach the negative y-axis, but never touch. Right? What's one more point that we could see? 2, 4. I'm going to replicate by going to 4, 2. It's pretty solid. So I took this point at 2, 4 and this point at 0, 1. I think we could have also used the point at 1, 2.
Yeah.
Would have been at 2, 1. If I make a really fat line,
Make a really big dot.
if I connect my grapefruits up here, life is good. Any questions on that? We handle the reflection okay?
Just pull them back.
All right, let's go on to example 4. It says the exponential function h of x equals a to the x contains the points 2, 3 and 6, 27. Find the average rate of change of y equals log base a of x over the interval from 3 to 27.
G of something. Right?
What in the world? Okay, so when I see it's talking about slope, that's a plus. You know how many times I've taught this in calculus this year, and I say average rate of change, and they say, huh? Average rate of change is slope. Yes. This is our y2 minus y1 over x2 minus x1. This is average rate of change. This is algebra 1 slope. Yes. But if h of x contains the points 2, 3 and 6, 27, then what do we know about log of x over the interval from 3 to 27? They're going to switch. So what are my 2 points? 3, 2 and 27, 6. Can we find the slope here? Surely. So y2 is going to be what?
6 minus 2.
We could do f of 27 minus f of 3 over 27 minus 3. What's f of 27? 6. 6 minus
2,
over
24,
Oh, I see.
Oh, I skipped a step. Oops.
which would be, what is it, 6?
Mhm.
Is that 1, 6?
Is that 9?
I think your room's too comfortable. I think your room's too comfortable.
Go push the air conditioner. Turn it down. It's hot.
It is hot.
Is that what you're saying?
Kind of. No, I just woke up, so.
Questions here?
Yeah, so pretty much you just do.
I did the same. It's all
And I like her. I like her. She has the bangs. That was good. I like her. Okay, but my mom,
All right, if you don't have any more questions, that'll be it. You have a homework sheet attached. Good luck. It should be pretty quick for you. It's not hard. Yes, let's check your other homeworks right now.